So far, we've talked a lot about vertical asymptotes. Now it's time to talk about horizontal asymptotes. Let's just approach this topic visually for a quick moment, and then we'll talk about the different type of asymptotes we can find. So if I just draw a basic rational function here, I'll just sketch, again, very roughly the base graph of f of x equals 1 over x. So far, we've talked about the vertical line that the function avoids. So in this particular instance, given f of x equals 1 over x, we know that the value of x the function avoids will be 0. In fact, the function is undefined at 0, and that's why we put in that dashed vertical line. But we also have a horizontal line that the function will avoid. Unlike vertical asymptotes, at times your functions can cross horizontal asymptotes, but you're still going to see them avoiding, for the most part, a horizontal line. So where do you see a horizontal line avoided by this function? And you're probably guessing, same as me, it's actually in this case just the x-axis. So in this example, the horizontal asymptote, so just like we can say VA for vertical asymptote, I'm going to say HA for horizontal asymptote. In this example, it is y equals 0. So in the horizontal direction, that's the y value the function will avoid. We're going to talk through different cases to understand how to find horizontal asymptotes. So in that way, they are a little more complex than the vertical asymptotes. Just to recap, for the VA, we just set the denominator equal to 0 and solve. So, equal to 0 and solve. So in that way, they're fairly straightforward, right? But with the horizontal asymptote, we're going to investigate 3 cases. So let's go ahead and take a look at those and make sure we feel comfortable. All right, so it turns out the horizontal asymptotes have to do with the power in the denominator as related to the power in the numerator. So 3 cases for finding these horizontal asymptotes. And the order of the cases doesn't really matter, so I'm just going to list them off as case 1, 2, and 3. So how about we call case 1 the case in which the degree, I can use the word degree of the numerator, so we understand degree to mean the highest power, is less than the degree of the denominator. So we'll make that our first case. And I'm going to give an example right away just to clarify. Denominator, if I can spell denominator, there we go. So in this case, automatically the horizontal asymptote will be y equals 0, automatically. So this is a pretty straightforward case. And we'll see why. So as an example, let's say that we were given f of x equals x plus 2 divided by x squared plus 5x plus 4. So we'll notice just real quickly that the degree of the numerator here is 1. We understand x in the numerator is raised to the first. And the degree in the denominator is 2. So we're in that case of 1 being less than 2. And if you think about it, when you have x to the first versus x squared, which term grows faster as the value of x changes? We would say that the x squared term grows faster, right? Because squaring a number makes it get bigger than just the number itself. So what's happening here is the denominator is getting bigger faster than the numerator. And so if you think about a fraction where the denominator is getting bigger and bigger and bigger, so just for sake of example, something like 1 over 10 versus like 1 over 100, right? If the denominator is blowing up, I won't talk too much about the numerator, but assuming the numerator is staying fairly small, that fraction overall will approach 0. And what the function approaches as x gets big in the both positive and negative direction is really what the horizontal asymptote is looking for. So that may be a teeny bit confusing at first, but as we keep looking at examples, I think it will clarify. So if I were to graph this function in Desmos, for example, I would see that at the ends of the graph, it's leveling off towards 0. So in other words, horizontal asymptotes look at the end behavior. And for that reason, we will study them again in calculus for those of you who take more math. So that is the first case, when the degree of the numerator is less than the degree of the denominator. Okay, the second case, we'll just look at these three cases again. So case 2, as you might guess, right? If case 1 was the degree of the numerator being less than the degree of the denominator, let's just flip that inequality around. So let's let case 2 be where the degree of the numerator is now greater than the degree of the denominator. So we're just flipping around the inequality. Okay, and in this case, I keep writing kind of our general assumption for each case. In this case, the horizontal asymptote is actually not a straight horizontal line. It's actually what we call a slant or oblique asymptote. And I'll graph one of these so you guys can see they're kind of weird. But we still can find what the asymptote is. So in our first example, right, when I was just graphing and talking about vertical versus horizontal asymptotes, they're actually, straight vertical or straight horizontal lines. But in the case of the second case of horizontal asymptotes, it'll actually appear more like a slant. So I'll just kind of attempt to draw a little idea of a slant asymptote. So I could have a function that does something kind of like this on one side, and then maybe kind of like this on the other side. So what's happening is the asymptote is slipping in right along this straight line here. So sorry for my poor sketch. I'll use Desmos to make it better, but that's the idea of a slant asymptote. It means there's actually a linear equation, right? Not just a horizontal line anymore, that tells us the line that the function avoids. So let's learn how to find the slant asymptotes. This is our second case that we're looking at, and it's the hardest case, I would say. So let's give ourselves this example. Let's say our function is 3x squared minus 2x plus 1 divided by x minus 1. So as you can tell here, the degree in the numerator is 2. The degree in the denominator is 1. So we're fitting this case because 2 is in fact greater than 1. So in order to find the slant asymptote, we're actually going to pull on our synthetic division skills from the past. So what we're going to do is divide, actually carry out the division that the rational function here implies, and then work with that result and interpret it as the asymptote. So if it's okay with you guys, I'm going to use synthetic division because from the feedback I've received, it seems like synthetic is a little more intuitive than the long division. So I'm going to place 3, -2, and 1 as my placeholders. If we have x minus 1 in the denominator as the factor, the corresponding 0 would be just 1. So we understand that we drop the first value, we multiply that with the number out front, so 3 times 1 is 3. That goes into our next column. We add down the column to get 1. I multiply again with the 1 out front to get 1, and it looks like our remainder is 2. So basically what's happening here is when we divide 3x squared minus 2x plus 1 by x minus 1, the result is, so if it began with an x squared, then this is our x and our number. So we've got 3x plus 1, and then I'll just go ahead and write the remainder real quick for us. The remainder is 2 over x minus 1. So through the division, we understand that to be the correct answer in terms of dividing, but the slant asymptote is actually just the result without the remainder. So the equation of the slant or oblique asymptote in this example will be y equals, because it does need to be a linear equation, and it's just the result of dividing without the remainder. So y equals 3x plus 1. So a little bit more work for sure in this case, right? We're pulling back our synthetic division from Unit 2. And I'll go ahead and pop out and graph that one for you guys just so we can start getting a little bit more comfortable. Slant asymptotes don't really come up quite as often, but I want you to feel confident finding them if needed. So I'll grab that graph and be right back. Okay, so I have the graph for you. In blue, you'll see I just plotted the original rational function. And then in green, I plotted the equation of the slant or oblique asymptote that we just found. And if I had this live on Desmos and zoomed in, you would tell that this green line again is approaching the blue line, but it's going to be the line that the blue function avoids. So it kind of looks like they're crossing maybe with how zoomed out it is, but that green line will be avoided by the function. So that's what a slant asymptote looks like. So again, I kind of did the hardest one in the middle here. We do have one more case for horizontal asymptotes that's going to be a little bit more friendly. So that was case 2 with your slant or oblique asymptotes. A little bit less common perhaps. So let's talk through case 3. I think you guys will like this one. So just to recap, so far in case 1, we talked about the degree of the numerator being less than the degree of the denominator. So we talked about the numerator being less than denominator. Then we talked about numerator being greater than denominator. So the only thing that's left must be what if those powers are equal, right? So case 3, I'm making our case 3 when the degree of the numerator is equal to the degree of the denominator. And in this case, the outcome of the horizontal asymptote will be pretty easy to establish. And I'll write it out as kind of a little formula here, and then we'll do an example. So the horizontal asymptote in this case will always be A over B, where A and B are the leading coefficients. That's a term we're familiar with from Unit 2, where A and B are the leading coefficients of the numerator and denominator respectively. So that's a little wordy, so the example will clarify what that's trying to get across. So we're basically just going to be stealing the coefficients from the numerator and denominator when the degree of the numerator is equal to the degree of the denominator. All right, this demands an example. So if we've been given f of x equals 2x squared plus 5x plus 1, and that's being divided, let's say, by all my scribbles here, 3x squared plus 7x plus 6. This feels like a fairly complicated rational function. There's a lot going on top and bottom, but again, I'm really focused on the highest degree in the numerator as compared to the highest degree in the denominator. 2 equals 2. So what we're understanding is basically the term with the highest power has the most power, right, as the value of x grows. So it's really just these front terms that matter most. So we're able to say that the end behavior approaches the ratio of these coefficients out front. So in this example, the horizontal asymptotes equation will be y equals 2/3. So asymptotes are always equations. And this would be the horizontal asymptote here. So any of these examples I just worked through that I didn't graph, feel free to do so just to see it for yourself. That's a little bit about horizontal asymptotes. I'll leave you with just a couple takeaways and then we'll move on to our next video. So while a rational functions graph will never cross its vertical asymptotes, it may cross the horizontal or slant asymptotes. So that's just something to keep in mind. So don't freak out if you graph it and you're like, oh no, it's crossing the horizontal. That can happen with horizontal. It cannot with vertical because if a function's undefined, it cannot touch that value. Another thing is, while a rational function can have many vertical asymptotes, right, just based on how complex the denominator is, there could be, 1 or 2 or 3, there will be at most one horizontal or slant asymptote. And that's based on the 3 cases that we learned in this video. So it is time to graph a rational function for ourselves. Let's hold off until the next video.